Thanks. I'll be in the order. Dear Heavenly Father, we thank you for the weekend just completed. We thank you for this day. Just pray that you'd just guide our thoughts and just give us clarity of understanding about chapter 2 and 3 of league groups, matrix league groups. And again, we thank you for your many blessings to us. In your name, Lord Jesus. Amen. All right. Well, so don't let me forget to collect your homework sometime.
Yeah.
You don't have to give it to me right this second.
I may have left it in my room.
Oh, you may have left it in your room.
And haha!
And it may not be entirely complete either.
No, it is complete.
Oh, it is complete, okay.
I just left it in my room.
Usually that's some sort of euphemism for...
It may have been completed a few hours ago.
Okay.
Me and Daniel are both one for one now.
Well, I will...
Or 1 and 1.
You can bring me the homework tomorrow, that's cool. So I spent hours, believe it or not, going back to the beginning and just reading back through, and most of it, I didn't really learn anything. I mean, it's like, yeah, okay, that's what we did, Okay, great, And then I got to chapter 2, everything's going all hunky-dory, everything's fine, understand. And then I got back to the proof of the simplicity of SO3, and I just tell you guys, well, he's sneaky here. He is sneaky here. This statement that if you look at phi from how's it go, SU2 to SO3, and what's his rule?
Phi of t is plus or minus t.
Yeah, that's lovely.
Yeah.
But you see, what I want you guys to find for me is the explicit mapping from 2x2 complex matrices, all right, to 3x3 real matrices, which what he means by that. Because the construction of those matrices is wrapped up in pages of discussion. All right? So that's one of your projects this week, is to find me this map. I will warn you, I don't think that's a trivial problem. I looked it up, and what I found, and it's fine if you guys want to look on the internet and try to digest something, pick your poison, whatever you want. You can try to work through what somebody else did. In fact, I would advise you to do something like that. I mean, you can try to do it from base principles, just using geometry. I mean, I tried to do that. I've tried to take like cosine theta plus u sine theta, and then just construct a rotation in SO3 by that angle around that axis through an explicit, like, how do you take that, thinking of this as a quaternion, and then take that quaternion and come up, pick from it the axis, pick from it the angle, and somehow use that to explicitly construct a rotation matrix. It seems like that should be possible without doing lots and lots of stuff like I've seen in PDFs, but and maybe it's not that hard, I don't know. But my impression, I've looked at it a little bit, I'm stuck on it at the moment. So I'm just going to leave that to you guys.
Can't all R3 rotations be a sum of 2 separate rotations about one axis? Like you can do every R rotation by 2 separate rotations. Like one about one axis, one about the other axis.
Yeah, I think that's true.
And so you could get each of those rotations from one of the columns of the C, maybe?
Yeah, I mean, work on it. If you can get an explicit map that does it, great. I mean, one of the things about it should be that it's if you look at the t here and if you look at minus t, they should map to the same thing.
Right.
All right, that's one of the things. All right, that's it. I'm going to try to do something more explicit here. And did I do this already? Prove that the reflection representation of isometries. Did I prove that any isometry of Rn that fixes the origin is a product of at most n reflections and hyperplanes through the origin?
Okay. What page?
I think we're going to do that.
I haven't done that yet. Okay, cool. This is on page 37. And so Oh, let me just erase that because I have this thing. Like I was saying, the result that SO3 is simple. In other words, that it has no non-trivial normal subgroups except for the whole group. There's a part of that proof which is very geometric. So what I want you guys to do for homework next week, in addition to the insidious T mapping, the phi mapping I was mentioning, was to go back and try to, if it's not too much trouble, work the homework from page 17 to 18. This is the, these are things about geometry, like they're about reflections and rotations. I think we need those problems understood in order to make sense of the simplicity of SO3 argument. It's more geometric than I realized.
So 1.51, 1.56, all the way through there.
Yeah. Like I said, page 17 and 18. Those problems. Some of them should be easy.
I did some of them in my first homework, not all of them.
So they weren't. Some of them weren't too bad. Okay.
And plus reading his proof for the simplicity of SO3 helped with some others.
Ah, that's funny. So it's like it's chicken or egg kind of thing. Like I'm saying it'll help with that proof, but you're saying that the opposite is true. Also, well, okay. In any event, all right. I'm trying not to give up on the geometry just yet. My heart is in chapter 3. Chapter 3, he gets much more algebraic and much less geometric, and I mean, part of me, the algebraist in me, just says, well, forget this geometric proof. Let's find an algebraic machine to show that SO3 is simple. I mean, I'm pretty sure there's a theorem not too long from now that a simple Lie group has a simple Lie algebra. And so, if you can show that the Lie algebra of SO3, little SO3, is not simple, it will then imply that SO3 is not simple. I think that's a theorem. But anyway, cart before horse. I'm trying to be, where I am and do what I'm doing. So let's get back to the geometry here for now. Reflection and representation of subgroups. Here's the theorem. Any isometry of Rn which fixes the origin is the product of at most n reflections in hyperplanes through the origin. Now, I think this is an example of these kinds of induction arguments I find slightly shocking. And, I mean, to me this is like, wow, induction is really something. Who would have thought that you could do an induction like that? I mean, you see these induction proofs in Matthew 100 or whatever about some hinky-dink property of even or odd numbers, and you're like, yeah, okay, great. But this to me is a non-trivial application of induction. It blows my mind that induction works for stuff like this. Anyway, n equals 1. We're gonna prove this by induction on n. So n equals 1, you've got R. What are the isometries of R? So you're looking F, what? F goes from R to R. It fixes the origin, right?
So f of t is equal to t or minus t.
Yeah, so you're like, well, okay, so what is f of,
Whatever it calls it.
I mean, we have f of AB is equal to f of A, f of B, right? That's the preservation of the dot product in one dimension. And f of 0 is 0 because an isometry has to be linear by another course. So I mean, in other words, f is linear. So I mean, what I really have is I have f of x is equal to, let's say, lambda x or some lambda. So this isometry condition actually gives you what? It gives you lambda times AB is equal to lambda A lambda B for all AB, right? In other words, lambda is equal to lambda squared. So this tells me what? This tells me lambda times lambda minus 1. Oh, I did something wrong. Huh. Why did I? Oh, I'm an idiot. What's the isometry condition?
F of A minus B is equal to F
Oh,
of A
I
minus
mean, sorry, t of x dot t of y should be equal to what? Right, it preserves dot products. So I've got an extra t here I shouldn't have, right? So like the dot product of A and B is equal to the dot product of the transformed A and the dot product of transformed B.
Right, preserve
This-
distance.
That's the condition for an isometry.
That makes sense.
Or one of the conditions anyway, I mean. Okay, so then that's better. So now I've got lambda squared is equal to 1, which tells us what? We get back to what you told me to start with, Daniel. Lambda is plus or minus 1, right? So therefore, f of x is either equal to plus or minus x. Those are the isometries. That's all the isometries that there are in one dimension, just plus or minus the identity map. So of course, minus f of, if you look at, let's say f of x equals to minus x, well that is a reflection. That's a reflection about the origin. It fixes 0, and that's it. On the other hand, if you look at the identity map, that's equal to f of x with my, let me call this f minus, and that's equal to f minus of x. So as you can see, product of at most, oh man.
Do we know that f is linear because it's an isometry? Or is it?
What? Yeah,
Okay.
I needed 2.
Is this going to be strong induction?
Product of at most n reflections. That looks like 2 reflections to me.
Well, it's either or. You're not gonna. The isometries are either x or minus x, which are both reflections. So it's just one, right?
Oh, I guess.
It's either 0 reflections or 1 reflection.
Oh, okay. So this is actually not. This is 0 reflections, and I just made it into 2 reflections because I'm a silly person.
Right.
Okay, so I didn't need to do that. The identities are a product of 0 reflections, and f of x equals minus x is just a reflection itself. So it's a product of 1 reflection, which is okay. Sorry. Yeah. That's why it's important to think about 0 reflections. Otherwise, this isn't true. Okay. So the base case is done, right?
Mm-hmm.
Okay. So now we suppose inductively that this is true. Suppose inductively for n equals k minus 1, and we'll consider, and then let f be an isometry of Rk, and let's say f not equal to the identity, all right? If f is the identity, we're done. It's since we figured this out now, it's the product of 0 reflections. Okay. Good, okay, I learned something today, good. Now if it's not the identity, what's that mean? That means that there's some vector v, right? So there exists a v and a w such that what? F of v is equal to w. W is not equal to v, right? If it's not the identity, right? There's some point that f outputs which isn't the same point. Make sense? So you can draw these things. I mean, here's v, here's w. I mean, whatever. This is a k-dimensional picture. So there's also something back here, u, U is V minus W. And you can you can define then the reflection in the hyperplane generated by U. So this is U. Let's say span of U for that notation if you don't mind. And then there is this thing, which I would say the hyperplane, the perp of it. This is, that's going to be essentially RK minus 1 inside RK, right? And we can define the reflection through the hyperplane. We can define this mapping. So like here, if I take this point X, then it maps over to here. So this is the so-called reflection through U. So RU of X, and what's the formula for that? This is not in Stillwell. I'm adding this. So here you go. You go minus X. All right. Minus X. But what you want is you want it to not do anything if you're along the U axis. So what you do is just add back that piece, but twice it. So back to X dot U hat, or U hat's the unit vector in the direction of U hat. There's a formula for it. This is clearly linear in X. And also if you feed it any scalar multiple of U, so check it out, like if I do RU of say K times U, what happens? You get minus KU plus 2 KU dot U hat. Oh, I'm sorry. I should really write KU hat here. Otherwise I'm being dumb. So KU hat would be a typical, U hat's the unit vector in the direction of U, so like KU hat, a typical thing in this, the line RU, a typical thing in there would be like some constant times U hat. So U hat, if you know what I'm talking about, Bradley?
Yeah, you have the unit vector.
Like this guy, right?
Yeah. So U dot U hat is
Yeah, so I'm missing some of the hats.
yeah.
So what we got is, we got 2, and that's of course 1.
Mm-hmm.
So I get back KU hat. So what this shows you is that if we take RU and restrict to this space, or if I can write it the other way, then I get the identity on, that line, right?
It's 4:00 p.m.
At this point, what he does is he looks at the composite of this RU with F. He says that, so RU composed with F, right, is what? If I feed this, if I put in KU into this, what do I get? Remember F is linear, so I get, no, how is F defined? F of V, right? U was what? U was a bit of a V minus W, right? So I do have to do F of that, right? I'll pull the K out. So I have F of V minus f of w, which is what?
W minus f of w.
Yeah. This feels wrong. I wasn't doing this earlier. I don't know why I'm doing this.
What are we trying to get to?
I'm following his proof at the moment. He argued, if I haven't copied it down wrong. I mean, we're trying. Well, neither W nor what is f of w? I don't know what f
We
of
don't know
w
what
is.
W is.
Yeah. I know that. That's not productive. Let me erase this. This is. I'm not sure if this is my mistake or me copying something down wrong. Or, I mean, everything I've said before that point I think is useful. The argument that I want to make is that if we look at. What I want is that RU composed with F, if you restrict that to the perp of U, I want this to be basically, I want it to be a mapping from here to here, all right? That's an isometry. Then I can use the induction hypothesis on that.
Okay, doesn't he say that RU is the reflection on the hyperplane U perp? Right?
Right.
So wouldn't that map KU hat to minus KU hat if it's a reflection?
Oh, shnikes.
So I think it would be X minus 2 X dot U.
Oh, I've got it exactly backwards, huh?
Yeah, I think so.
Oh, thank you. Very good, very good. Yes, that's right, that's right. I'm an idiot. So the reflection fixes everything that's in the hyperplane, and it
Mhm.
turns everything else over. So it's exactly the opposite of what I wrote. So sorry. Goodness gracious. Of course, it's still the case. Ironically enough, this is almost the same, right? But I mean, the set theoretic statement is still almost true. It's minus identity, right? I mean, it's still the case that the span of U is an invariant subspace of the reflection.
Mhm.
It maps that to that, but it also.
It just switches it.
Oh, okay. So then it's the identity on the. Now that makes more sense than to say that. So if we. I still don't know how I know how. Well. Curses. Try not to spend too much time on this. I'm failing. He says, the reflection RU in the hyperplane orthogonal to U equals V minus W maps the space RU onto itself, and the map RU F, F followed by RU, is the identity on the subspace RU of RK. Right, so that's another claim he's making. He claims that if we look at RU, composed with F, acting on some multiple of U hat, right? then he says that that's the identity on RU. That should have to do with the definition of the V and the W and everything. All right, so great. I could rewrite this, of course, as RU f of some constant lambda times u. Who cares what the length of u is, right? Let's work in terms of u, not the u vector. And then what? So I pull out the lambda, right? And what's f of u? U is v minus w, right? So f of v minus f of w, since u is equal to v minus w. I'm not reading it wrong, so is that right? Correct?
I think so.
Yeah. All right, so then what? Of course, this is what? This is f of v is equal to w. F of w, I know what f of w is. I'm sorry, I don't see how he sees that that's... You guys see it? I don't see it. I'm sorry, guys. I don't. No, but anyway, if I can, I'm not sure. Maybe it's a typo or something stupid. Why does that matter to know that that's the identity? I mean, what he really wants, of course, is that this is an isometry, right? I mean, that's the interesting thing, I think. And the reason that's an isometry is it's the composite of isometries, right? Reflections in isometry. F is assumed to be an isometry, and if you restrict it, it's still an isometry. How do you know that this is? How do you know that this is still in the? How do you know that doesn't map onto U? I'm going to go on, you guys. I'm sorry. I'll have to think about this more. And I have thought about it. I just apparently didn't think the right thing. I don't know. Once you know that's an isometry, then what can you do? You apply the induction hypothesis. So that's a product of, this is basically RK, right? K minus 1. So you get that this is a product of, at most, K minus 1 reflections. And then you can just solve for F. And because the product, and you take RU of both sides, basically, and then you get F as a product of K reflections. And that's the induction, and then the other induction true. So obviously what we're a little bit, obviously like a lot shaky on at the moment is proving, in fact, that that is an isometry which takes the perp of U as an invariant subspace. Right. And likewise, so there's, well anyway, there's 30% of the proof. I'm sorry guys, I tried. I failed. This is an interesting theorem though, right? He said this theorem is sometimes known as the Cartan-Dieudonné theorem, after a far more general theorem proved by Cartan in 1938, and a generalization by Dieudonné, which I'm mispronouncing. You can fix it for me, Daniel.
Dieudonné.
There we go. because he did that over spaces with coordinates from finite fields. That's hardcore. This is a very interesting thing, though. I mean, so basically, reflections are enough. If you understand reflections, you can build rotations from reflections, is what this is saying. Which is a very interesting result, right? Okay. Sorry to have wasted all our time on that. I will try to redeem myself in what follows. No. This is always dicey. See, all of this stuff is words in here, right? He doesn't have any formulas, so we can't.
Right.
I mean, I don't doubt that he's right. I just, I would like to be a little bit more explicit in a class like this, you know?
I'd like to see an example of that. Like,
Yeah, well, that's the next section. So here, basically, the point is rotations of R4. So let's apply that theorem to R4. A rotation of R4 has to be a product of reflections in R4, up to 4 of them, right?
Mm-hmm.
Is the point. And so, first of all, he shows that a reflection through the hyperplane, through the origin, orthogonal to the unit Quaternion U is the map as follows. So if I'm in R4, which of course is the Quaternions, right? And I've got, so here's my origin, right? Here's U. So he's like a reflection through that hyperplane is the following map. This is Q maps to minus U Q conjugate U. All right. Now, let's see here. Maybe we'll have more success with this calculation. I don't know. Let's find out. First of all, does this? And let me give this thing a name. I hate these. And what's he has something against naming things. I don't know. Let's call that phi.
Did he say somewhere that it has to be a product of even number of reflections? That's less than or equal to?
For it to be a rotation.
Yeah, for it to be a rotation.
For it to preserve order.
Yeah, for it to preserve orientation.
Oh yeah, orientation.
Yeah. So this phi of Q is minus U Q Quaternion conjugate U, right? So first order of business, what happens to U? Phi of U is what? First of all, this is linear, all right? Because the quaternionic conjugate is linear. Real linear is what I mean also. Okay, so phi of U does what? This is minus U, U conjugate U, right? Now this was what? This is assumed to be an element of S3, I believe. It's one of the unit quaternions, so that UU bar is what? Just 1, right?
Mm.
So this is minus U. That's a good sign. We map, we map U to minus U. Now what makes up, this is interesting, what makes up this three-dimensional hyperplane, or you could call it a hypervolume, like this space, right? Is you got like IU, you got JU, you got KU. I think that assumes U is not equal to, oh no, what would happen if U is equal to IJ or K? One of these becomes the real axis, it's still fine.
Yeah.
So the point is, these are linearly these are orthogonal. In fact, you can check that IU, JU, KU are orthogonal to U. Well, are these orthogonal to U? Man, I hope they are. How can I check that?
Shouldn't they be by definition?
I don't know. No, what's u times iu is what? Or how about this is minus iuu, right?
Right. So minus iu squared, so it shouldn't just be I? Or am I...
How did that go? Remember last time? So we have is u squared is minus u dot u plus u cross u by the general quaternionic identity. If this is 1, this is minus 1, right? So this is straight up minus I times minus 1, which is I.
Okay, so it is.
So this, by the way, is 0 plus I. In the sense that u times iu is equal to u dot iu, with a minus, sorry, minus, just be careful, plus u cross iu, right? So from this I can deduce that in fact u cross iu
Equal to 0.
is equal to I.
Right.
And u dot
I 0.
iu is 0, which means it's orthogonal.
Mm-hmm.
So consequently, iu is an element of perp of u. But the same, almost the same
So it's
argument
Ju and Ku.
will work for ju and ku exactly.
So where there can be so many perps in our...
I know you have 4 dimensions, and a lot of wiggle room in R4, isn't there? Okay, so you guys agree, because of this calculation and a similar pair for j and k, the perp of u is the span, the real span of iu, ju, ku.
Yeah.
Okay, so then if I look at phi of, say, c1 iu plus c2 ju plus c3 ku, what do I get? I get like c1, and then I get, let me pull the minus. I tell you what, this is obnoxious. Forget that. Why do that? What am I doing?
That we get.
Let's focus on the basis. Am I doing it for a vector? I can do it for a basis. What's phi of iu? It's minus u, quaternionic conjugate of iu, right? And then u again, by the definition of the phi map. But the quaternionic conjugate does what?
That
Makes it negative. Or
keeps the imaginary
switches.
exponent the same.
Switches the order, right? And it switches that in minus I, right? Yeah. Like that? Is that what you're saying?
We should switch the order of the real components and keep the imaginary the same. Is that what?
For the product of quaternions, Q1 and Q2, the conjugate of Q1 and Q2 is Q2 conjugate, Q1 conjugate. But the quaternionic conjugate also changes I to minus I believe. I mean, it's, like you said, it keeps the real real, and it swaps the pure imaginaries to minus what they were. So that's
Okay.
that's this.
Yeah.
But this is 1.
So you just get IU.
Yep. And so, as you can see, IU is a fixed point of phi. And in fact, you can show any point on this plane maps back to itself under phi. Which goes to show, of course, that this mapping phi is a reflection on that hyperplane. All right, so I can do the easy theorems.
It's a reflection. Is it zero reflection? Or is it just...
Well, the point is that this is a reflection, which it's a reflection for the hyperplane with normal u, basically. And that brings us to the next result, which is the interesting one. The quaternionic representation of rotations So this is on page 39 of Stillwell. Any rotation of H, which of course is R4, about the origin, or about, if you're Canadian, is a map of form Q maps to V, Q, and W, where V and W are unit quaternions. Which, as we've discussed, is the pretty sphere. So this is a combination of that Cartan theorem and and this. So the point is, if you've got a rotation of R4, it's an isometry of R4, right? So it's a product. It's a orientation preserving isometry, right? Reflections reverse orientation. So that means you either have 0, 2, or 4 reflections forming this isometry. But we know that the reflections look like this, right? So you either have the mapping, something like basically Q maps to what? Just Q maps to Q, okay, which is a stupid form of this map, 0 reflections. Or you have something like it is two reflections, right? So it's like something like U1 minus U1. You can question my ordering, whatever. So you've got a reflection and then another reflection. But as you can see, the minuses cancel, and you're just left with what? U1, U2, U2, Q, 2U1. But this is just V and this is just W.
Right, also the conjugations cancel. Or
Let's say, what's the difference between a conjugation and a reflection?
Oh.
it's part of the definition
Oh
of
my goodness, yeah, I forgot something. So this is conjugate and then
That whole thing is conjugate.
yeah, so I sorry, yeah, that's an important detail. So this, of course, is U1, U2 conjugate, Q conjugate conjugate, U2 conjugate, U1, which is U1, U2 conjugate, Q, U2 conjugate, U1. And that's what I should think of as the V,
Right.
and that's the W. And the same for 4. Same, oh, sorry. 4. You don't get to say 4 that much. Strange what I did. I wasn't ready for that. All right.
I would not be happy writing out 4.
Just be happy I didn't write 44. Let's see here.
22 lines all stacked on top of each other.
Now, so there you go. Any rotation of R4 is a product of, it's a sandwiching of two unit quaternions like this. The thing we did last time was a rotation of R3 inside the quaternions, which we got as conjugation of a particular quaternion, right? That's a different thing. Last time we were looking at rotations of R3 inside the R4 of quaternions, right, by conjugation of quaternion multiplication. This is a 4-dimensional rotation, something less familiar, nevertheless obtained from a pair of quaternions. Now, the next order of business is to say, well, okay, is that unique? Almost. We also have to argue the converse direction, of course, which is that mapping actually is a
Rotation.
yeah, rotation. It's clear enough that it's an isometry because of arguments like we looked at even back for the complex case. The multiplicativity of the norm gives it's an isometry really. And the orientation preserving, it looks like he's just really arguing that if you look at the matrix of this, if you look at the matrix of this, you get this thing. You know,
Takes it.
which has determinant 1. So, and so since you have 2 of those, bless you. Since you have 2 of those, it's determinant 1. Basically, this is really, well, I don't know. Anyway, you can show that this is in fact orientation preserving. I don't feel like doing that at the moment.
Yeah. He doesn't always show things, just kind of like, you can generally see it just kind of works.
Well, some things are left to the reader. I mean, he does have an explanation there. I mean, even as a formula. What he's saying is that if you look at the unit quaternion, right, and if you look at the corresponding linear transformation on R4, then you can see the determinant of that 4x4 matrix is 1. So there's some isomorphisms being used here. So he's well, fine. Now you got me. Now you got me wanting to do it. Great. Look what you guys did. Fine. You've harassed me into thinking about it. It's all your fault, Brendan.
I didn't say anything.
I'm going to regret this, but I don't have time to talk about the more interesting stuff. All right.
Get to chapter 3.
I know, right? So, what's going on is, on the one hand, Q is a quaternion, but on the one hand, Q is an R4 vector.
Yeah.
So, you can either look at it as a... but you could look at quaternions as 4x4 real matrices. You could look at them as 2x2 complex matrices of a particular type. So, if I think of this as, say, being the mapping phi of, and let me just say Q vector for a 4-dimensional vector, then this is equal to the matrix, all right, of the matrix of V times the matrix of Q times the matrix, times this. I think something like that might get away with, we might get away with that. So like, these are 4x4 real matrices which correspond to the quaternion.
Why don't we do matrix of W? Why don't we do matrix of W?
Well, I wanted another, I don't know. I wanted it to go from R4 to R4. So this is like 4x4, 4x4, 4x1. So, but I don't know, you could go that way too, I guess. Fine.
Or couldn't you do like
You talked me into it.
the matrix and then have something that goes from the representation to...
So this would be the matrix of
Yeah, exactly.
Yeah. So orientation is not something you can really see for a specific point. Orientation is something you have to study a basis for. It has to do with the relation between a set of vectors in the space, not just one vector. In other words, we take a right-handed frame to a right-handed frame. So the point is, if you look at the determinant, how to say that even? I don't know. So if I do this for not just one vector, if I do this for a bunch of them, right? Like, I don't know. Let's say j equals to 1, 2, 3, 4, where that's a let's say a positively oriented frame. In other words, that would mean the determinant of Q1, Q2, Q3, Q4 is, and let's suppose it's orthonormal, so this is equal to 1. So 4x4 matrix made of gluing these together. Then if I look at the determinant of the corresponding image of those, right, then what I'm going to get once I do things correctly is basically the things I already have, and then products of these guys, which are 1 because the determinant of the unit, I mean the determinant of these guys is the length of the quaternion, which is 1. There's more I need to say for this to quite make sense. I'm sorry, it's taking me too far afield. Well, now I have something else I need to write up. Urgh. All right, anyway, the point though, right, is just that we have any rotation as this kind of sandwiching of unit quaternions. And he also points out as we read on that you get the same map if you trade V and W for minus V and minus W. Okay. Okay, so next. Dang it, I wanted to get Jeopardy. All right, so next he talks about direct product of groups. Which is something easier than what we've been doing. So like G cross H is just what? It's the set G comma H such that G is in G and H is in H. And how does they work? Like if I have GH times AB, how does it work? It goes GA HB. He points out, of course, you know, some obvious examples. Like this is how we take the direct product of vector spaces. You know, if I have the vector space V and a vector space W, I take their Cartesian product. I can also think about that being their direct product in the sense, I usually would say direct sum because the multiplication is actually addition in that case, so it's kind of, but this is an interesting example here.
Like the plus sign with the circle around it better.
Yeah, but here's an interesting example. He's like, okay, so Rn, I mean rather R, he said is isomorphic to 2x2 matrices like this, right? So this is R with addition, I think. So let's see how that gets kind of weird. You see, these matrices convert addition in R to multiplication of matrices. Let's see how that goes. Let's see her multiply the matrices. What do you get?
X plus y.
No.
Oh,
You get,
where are we?
you get y plus x. Sorry, Daniel. Just fulfilling my jerk quota for the day. But so yeah, that's kind of weird, right? Because this addition of real numbers has become multiplication of these matrices. And then he's like, so R2, which of course is R cross R, and simpatico with this notation, it's the additive. You do add in each component, the additive group. So that actually is isomorphic to the direct product of these. So if I call this thing, let's say G, right? Then this is like G cross G, which, as he points out, you can look at as block matrices. Stuff like
Zeros.
yeah, zeros.
Hey, that's like chapter 1 of Advanced Calc last year.
Uh-huh. So there is an incredibly inefficient notation for this. But it's fun. And then, of course, most interestingly, we talk about the tori. T2 is S1 cross. I can't draw his
His S's are impossible to write.
yeah, his S's. I have not mastered that yet.
Yeah.
Something like, yeah,
It's like Superman.
right.
So that's what T2
Not there
means.
yet. I'm gonna figure out how to draw that though. But yeah, that's the donut. I should have brought donuts. There were donuts in the mail room.
Okay. Well,
Might see.
I had a hypothesis on what T2 meant, and it ended up being the same kind of thing as that,
Yeah.
but it's a little different.
Yeah, I wanted to check, but
I couldn't check. There was nowhere else in the book that it said
My
it.
page on T2 was the same.
Oh, is that what it was?
Oh, you're missing a page?
I'm missing a few pages, yeah.
In the printing, it just like randomly skips some pages?
Yep. But I found the PDF online, so I
Uh,
feel justified in doing that now.
well, I guess it's just teaching us that we should really download books rather than buy printed copies from Springer. Not really the kind of lesson
Yeah.
they should be teaching us, but oh well. No, so these things will happen. It makes an interesting comment here.
Interesting.
The reals and the unit circle are abelian, right? In other words, group multiplication is commutative. And the same is true of all their direct products. So like the direct product of abelian groups is once more abelian. In particular, like Rm cross Tn, where Tn is the n-torus, formed from the Cartesian product of n-fold copies of the unit circle.
Yeah, so
In fact, this is interesting, they include all the connected abelian matrix Lie groups. So it's either a copy of tori or a copy of Rn sitting in there, something isomorphic to that.
So why are they calling the torus two-dimensional? Is it? It ends up being three-dimensional, doesn't it?
T2
Yeah, T2.
is two-dimensional. It takes you give me two angles.
It's like saying a sphere is two-dimensional in R3. It's like a two-dimensional
It's
surface.
It's not a solid
It's
donut.
It's not a solid,
It's
yeah.
not a solid donut. It's just the
It's a
glaze.
surface.
Oh, so that's what that counts?
Yeah.
Because S1 is the unit circle, right?
Right. I mean, the point is, if you give me a pair of angles, right, theta beta, then that maps to this, e to the I theta comma e to the I beta, and that's, that's a point on the torus. Well, one representation of it. I mean, you can look at I'm looking at the torus inside a copy of. I'm looking at the torus as a subset of C2. Of course, you could also geometrically put it in R3, as I did this morning in Calculus 2 when they asked me to calculate its volume.
Right. So it looks like it's R3. Yeah,
Same way a sphere does.
I'll look at it.
Yeah. Now, all right. So he's like, all right. So we can just as well put a V inverse here, right? Because why not? I mean, it's a unit quaternion, so it has an inverse. You can multiply. Just call it the inverse of V instead of V, just relabeling. And the reason he wants to do that, several facets, but all right. So so let's see here. He said we're going to look at then is basically S3 cross S3, where we have unit quaternions, say U and V, times other unit quaternions, say W and zeta, I don't know. That looks like a Z. Let's see here, so then it's just UW, VZ, whatever. So the direct product of unit quaternions.
Mm-hmm.
So these form a group under the operation, like I should say there. And they're, it's again S3 and S3 because the product of things in S3 is in S3 again. So